screen, and you can see the screen. So this particular short-term course is on fluid mechanics, and I wanted to talk about not only fluid mechanics but also some of the applications which we have been working on in this particular lecture. And so you will see that we are going to talk about microfluidics, and there is a two-phase flow problem. Let us look at the topic first: sustainable process for continuous synthesis and separation of silver nanoparticles. AgNP is basically silver nanoparticles using ATPS. So ATPS is nothing but an aqueous two-phase system. So normally in chemical engineering, whenever we talk about a two-phase system, you have an organic phase and an aqueous phase, an oil phase and an aqueous phase. But ATPS is something which is where both the phases are aqueous, okay, and they are immiscible. So this is the nice thing about ATPS. The reason is we want to avoid using organic liquids because they are toxic, carcinogenic, and they are basically causing environmental problems. So if you want to move towards the sustainability, you want to make sure you don't use any organic fluids. So this is the idea. This was the motivation for the work. This work was basically done by my PhD student Vamsi, who is now a faculty at IIT Hyderabad. Okay. So by way of motivation, I mean most of us know that these nanoparticles are very well researched area. Okay, and we wanted to basically do something which is not only do the synthesis but also separation. We will see the details of that. So the reason why you want to go for nanoparticles is because the chemical properties, the physical properties and the chemical properties at the nanoscale are completely different from what you get at the bulk. And the specific surface area, the surface area per unit volume is very high for the nanoparticles. So surface area per unit volume for a spherical particle scales as 1 by R. So R is less, the surface area per unit volume becomes large. And we are interested in metallic nanoparticles because they are used to making things like conductive ink, enhancing thermal conductivity. They can be used as catalysts. So these are applications which we have for silver nanoparticles and copper nanoparticles. We're looking at metallic nanoparticles. Okay, and whereas when you look at physical properties, the melting point of copper is around 1085, for silver is 960 Celsius, and the melting point of these nanoparticles is much lower. So these are some of the physical properties I wanted to basically make all of you aware of. Okay, and this is what we're going to talk about in the synthesis part. Now, we want to synthesize these nanoparticles in a continuous manner. We don't want to do the synthesis in a batch process. So when you talk about synthesizing in continuous, the very common reactor which comes to our mind is the laminar flow reactor. And in the laminar flow reactor, which you see, you have the velocity profile which is parabolic. So you have this parabolic velocity profile, and you add in the, as far as the reaction is concerned, you add the silver nitrate, which is called the precursor, and then you add a reducing agent, which is something like the sodium borohydrate, which is the one which is going to reduce the silver ion to silver nanoparticle. So you need two reactants. One is the reducing agent, which, for example, there can be many reducing agents, but let us say sodium borohydrate, and let us say the silver nitrate is the nanoparticles. So these are both introduced at the inlet on the left, and we are focusing on continuous synthesis. So the reason is, like I said, we want to have better control of the product quality. Batch synthesis, I mean, there can be variations from batch to batch. Okay, and the other thing that we want to do is we want to look at flow in a microchannel, because the flow in the microchannel is well defined. It's laminar. This is as opposed to doing it in a big channel where the flow is turbulent. Okay, and if there's turbulence, the mixing is not going to be uniform everywhere. So you will have variations in the properties and sizes of these nanoparticles. So that is what I'm trying to show you on the right hand side. This is a typical example of what is called a residence time distribution. And experimentally, if I in the top figure on the right, if I give a pulse input at the inlet of my reactor, because of the parabolic velocity profile, there is going to be a dispersion effect. And what comes out at the outlet is going to be spread out. And so when I give a pulse input, which has a very narrow distribution, because of this dispersion, I get a very broad outlet distribution. So basically what this means, and similarly if you want to give a step input, which I'm showing at the bottom, you will see that you don't get a step response. So if your reactor had been a plug flow reactor where the velocity profile is completely flat, then you will get whatever you give as input will come as output. But because of the laminar flow conditions, you get this dispersion. Okay, and there is a lot of axial mixing going on, which gives rise to the spread. Now this spread is going to have a problem. So if you look at the velocity profile, in the middle the velocity is very high, and in the near the walls the velocity is zero because of the no slip boundary condition. So the reactants which are present in the middle, they will spend lesser time in the reactor because the velocity is high, and therefore the amount of reaction in the central portion is going to be less. There's an echo. Yeah, and the reactants near the wall are going to spend a lot more time. So this is not desirable. Why it's not desirable? Because then the particle size distribution is going to be very broad. I mean, we want to produce as far as possible a very narrow size distribution of particles. Okay, we want all our particles to have the same size. But if we have a parabolic velocity profile, because different fluid elements are spending different times in the reactor, they will have different sizes of particles coming out. So how can you avoid this problem? Because I want to have a millifluidic channel or a microfluidics, and I want to go into multi-phase flows. So why are we using multi-phase flows? The flow in the microchannel, like I told you earlier, is laminar. And just give me a minute. Yeah. So the flow in the single phase flow is laminar. I have the parabolic velocity profile, and your residence time distribution is very broad. So how can you overcome this problem? So one way by which you can overcome this problem is by having a two-phase flow, and that is what I'm showing you in this figure. So this is just the one liquid which is coming in, a carrier fluid, which forms the continuous phase, and the blue and the red are basically two reactants, which is maybe the reducing agent and the precursor. Okay, so what happens is, if they are immiscible, you will get these kind of drops or slugs. So you see on in the channel, after they enter, you see there's a red portion and the blue one cylinder or an oblate spheroid, where top half is red, bottom half is blue. So those are the two reactants which I'm sending in, and these are basically slugs which are traveling throughout the reactor. So basically this is an example of a segmented flow or a dispersed flow. So we have a dispersed flow or segmented flow, and in the segmented flow you have basically good mixing. So one way to look at this problem is to say that each segment, each slug is behaves like a microreactor. Each drop is going to behave like a microreactor. The reactors are inside and there is mixing. So each slug is going to travel in this microchannel, and it is going to spend the same amount of time in the microchannel. Okay, and this way in each slug I will get nanoparticles made, and the nanoparticles made are going to be uniform in the size and properties, because the mixing inside each slug is going to be the same for every slug. There are many slugs, and each slug will spend the same time in the reactor. So this is the major point. So we are avoiding the problem of different fluid elements spending different times in the reactor for single phase. And so this we have each slug behaves like a microreactor, spending the same residence time, and I get the same conversion, same performance. So this is what people have been doing, and the only idea is that these are two immiscible liquids. The white region is maybe an organic phase, the blue and red may be an aqueous phase where the reaction takes place. Okay, and so what I'm trying to show you here is that by going from single phase to multi-phase, we can get a narrow size, narrow residence time distribution, and a narrow size particles. Narrow size distribution in the size of the particles. And yeah, but like I said, there's a problem. One of them is an organic phase. Existing methods, they use, one is an organic phase and the other is an aqueous phase. Okay, and if you want to make these nanoparticles with specific applications in biomedical engineering, then one has to avoid the use of organic phase. So because of the use of organic phase, these nanoparticles will have limited applications, and therefore we are going to look at aqueous two-phase systems. Okay, in the aqueous two-phase systems, both the phases are, the slug flow is basically got dispersed phase. So I'm showing you two pictures here. In the first one, there is a slug flow or a dispersed flow, and this has low capillary number. And in the second case, you have a parallel flow where the two liquids are flowing side by side, and this has got a high capillary number. So this dimensionless number, the capillary number, tells you the ratio between the inertial forces and the surface tension forces. So if the capillary number is low, that means the surface tension is very high. Okay, and therefore the liquid breaks into slugs, and you see this flow. If the high capillary number, the surface tension is low, and we have a parallel flow. Inertial forces are high. So this is the basic idea. Now, one problem you have in aqueous two-phase system is that these systems have a very, very low interfacial tension. Now, for the water and air system, the interfacial tension, surface tension is 72 dynes per centimeter. Now, for aqueous two-phase system, it is about 1,000 times lower because both the phases are aqueous. Okay, and so what that means is it is, and we wanted to go and have the slug flow reactor. We wanted to have a slug flow, because only then we can have this internal mixing. Now, I wanted to tell you why we have the internal mixing in the slug. It's because the shear stress which is you know uh, imposed on the slugs, and because of shear stress you have the internal circulation. Now, what we want to say, I want to say here is that the surface tension is very low, and therefore we always will have a very high capillary number. Okay, and therefore in aqueous two-phase system it is very difficult to get parallel flow, and you can get parallel flow only if the flow rate is very, very low. Sorry, you will get slug flow only if the flow rate is very, very low. Okay, uh, so you need to have a very, very low flow rate to get slug flow, and our objective of interest is slug flow. And if you have a very, very low flow rate, then you will not be able to get enough nanoparticles produced, because the throughput is going to be very less because the flow rate is less. So and of course it is also very difficult to control things at a very low flow rate. Okay, it is not easy to control things at a low flow rate. So now, how do you overcome this problem? So this is just to give you an idea about the properties that I was talking about. We have a castor oil water system, that is the organic aqua system, and then I have an ATPS system. Now, to tell you what is an ATPS system, there can be different combinations of ATPS. Usually, it could be polymer, or it could be polymer and salt. So we have given you an example uh, here of a PEG, which is the polymer, polyethylene glycol, and citrate, which is the salt. Okay, and what I wanted to show in this figure is what are the kind of capillary numbers that we have. So idea is that if you wanted to work with a microfluidic system, okay, where the channel diameter is about 100 microns, okay, you see that for the flow rates, the capillary number in the oil water system is 1 and 10 and 3 and 37, depending on the flow rate. But if you go to if you were to go, and what we want is lower capillary number. So, but if you go to the milli channel, that is, you make the channel slightly bigger. Instead of 100 micron, make it 1000 micron or 1 millimeter. Then you see that your capillary numbers are actually going to be lower. The capillary number is about 100 times lower. So, and we want low capillary number. Only then we can get slug flow. So, one way to overcome this problem of getting slug flow in ATPS is to not work with microfluidics but with millifluidics. Work with not 100 microns but 1000 microns. So then it becomes much easier. So this is one of the main things which my PhD student Vamsi found out, because he was struggling a lot with the getting a slug flow in the ATPS system. Okay, he was struggling a lot, and finally he went back and he looked at, how can I change the reduce the inertial effect and improve the surface tension force. So, and a very simple change he made. Instead of going for a 100 micron system, he went for a 1000 micron system, diameter channel. and this calculation on the right. So basically, I'm trying to show that the fundamentals are very important when you're doing these kinds of flow problems. So organic aqueous systems, the surface tension is high, and there it is easy to get slug flow in a microchannel. But in aqueous two-phase system, surface tension is very low. You can only get parallel flow. But if you go to millifluidics, and in millifluidics also you will have a very well-defined hydrodynamics. You will get slug flow with internal circulations, and you will get this kind of a behavior. This is some basic thermodynamic information which I'm showing for the pig and citrate system. This is like a phase diagram. You see the solid line, which is basically called the binodal curve. So above this binodal curve, if you have a composition in your liquid, you will get a two-phase region. So that is what I'm trying to show, that you will get a two-phase region when you are having a composition above the binodal curve. So all this dashed line you see the circles. Okay, you take a composition which is 12% of PEG and 12% of citrate. You are going to be above the binodal curve. So if you mix and make a solution, aqueous solution containing 12% citrate, 12% PEG, okay, that's the operating point. You will get a two-phase mixture because you are above the binodal curve. One phase will be rich in citrate. The dashed red line you see is basically the line which is a tie line, which is very similar to what you see in a VLE diagram. Okay, and one phase will be rich in citrate, another phase will be rich in PEG. So basically, that when your overall composition is above the binodal curve, you get two phases, one rich in PEG, one rich in citrate. Okay, but if you are below the binodal curve, you will get only a single phase region. You won't get two phase. So if you want to have a two-phase system, you have to choose your composition of PEG and trisodium citrate as the lying above the binodal curve. If it is going to lie below the binodal curve, you will have a single phase flow and you get only laminar profile. So that is an important point. Okay. So we are interested in, we don't want single phase flow because there I have the laminar profile and the residence time distribution is very broad. I want to have a two-phase flow, so I must go for this thing. Now, why did I choose PEG and TSC? Because trisodium citrate and PEG both act as reducing agents. So if I want to do some nanoparticle synthesis, I can do the synthesis with this particular ATPS, which contains PEG and trisodium citrate, which act as reducing agents. So if I add the silver nitrate, it will get reduced to silver nanoparticle. Okay. So this is as far as the hydrodynamics is concerned. What you see here is I'm giving you the hydrodynamics for pure PEG and pure TSC solution. See that you can get different kinds of flow patterns. You can see the single phase is of course the red thing. So on the right you see what I call a flow regime map. Okay, and the flow regime map is telling you the different kinds of flow patterns that you will get when you have for different flow rates of PEG and trisodium citrate. So trisodium citrate and PEG are the two inlets which are pumping into the reactor. Okay, pure PEG solution with dye is added, pure TSC solution is added, and when it is added, it flows to the microchannel, and then you take an image of what is happening in the microchannel. you can get long slug. So there are different kinds of flow patterns available. And what we have done is we've just classified the different flow patterns, whether it's jetting, wavy, core annular, whether it's stratified flow, single phase flow, slug, long slug, etc. So we classify this because what do you want? Well, this is an experimental study. What do you want? You want to basically, when you want to synthesize the silver nanoparticles, you want to operate at a point where you have the slug flow, where you have the internal circulations possible. Okay, so in the two-phase flow, the slug flow is what we want, because there my slugs are all going to be of the same size and they spend the same amount of time in the reactor, and I get a uniform size particles. So that is the idea. So this is basically what I said earlier also. We are going towards a milli channel because I'm going to get slug flow with a reasonable throughput, with I'm not at a reasonably high flow rate. See, when you increase the flow rate, what happens is the inertial forces become dominant. The surface tension forces become less. Now, as it is, the surface tension is very less in the system. Okay, so we need to therefore make sure that when I increase the flow rate, I still have my surface tension dominating. And one way to do that is to go to a milli channel, and that's basically what I'm explaining here. Okay, so the way you do the experiment is you have these two syringe pumps on the left. You pump the two liquids. One is the PEG and one is the trisodium citrate, and you look at the flow inside, and you see that you have a segmented flow. And you can, basically characterize the thing. So look at what is coming out of the reactor, and the top phase will contain the PEG rich phase, the bottom phase will contain the TSC trisodium citrate rich phase. So basically to tell you that indeed there are two phases in the very clear meniscus. Okay. Now what happens is, I told you, you will be pumping in solutions with earlier I was pumping the liquid which had pure PEG and pure citrate. So what happens is, you need to get an equilibrium between, because the PEG is going to form the PEG rich phase, and there will be one phase which is the citrate rich phase. Okay, and so there's a mass transfer which takes place in these systems. What we want to do here is pump in. What I'm doing here is pumping in the equilibrated solution. That is, what is the equilibrium composition when you are in a two-phase region. Those are the two ends of the tie line where it cuts the binodal curve. So you take I'm pumping in the PEG rich solution and the citrate rich solution. What I get here is basically slug flow, okay, which is basically what I want, because my system is now at equilibrium. And now you see there's a transition region also, and then I have the core annular flow, which is my stratified flow. So if you were to pump the equilibrated solution, you have only three possible flow patterns: slug flow, the transition flow, and then you have the core annular flow. Okay, and so this is what we have. So now if you want to work in a slug flow regime, you can use this flow regime map and say, look, I will choose my flow rate for PEG to be 40 and for citrate to be 20 microliters per minute, and then pump my liquid. I'm guaranteed to get slug flow, because that is how I want to do an experiment. Okay, where I can get uniform size slugs. So that's what I'm trying to show. The uniform sludge flow means uniform sludge, which you see in the middle of your slide on the left. Okay, then you have the transition. The slugs are becoming non-uniform. They're joining, and then finally all the slugs join, and you get the core annular flow. This core annular flow is my stratified flow. Okay, so I just want to share that if you have equilibrated solutions of PEG and trisodium citrate, which are pumping in, there's no mass transfer going to take place, and then your flow patterns become uniform. Okay, so basically, rather than work in terms of dimensional values, where you talk about flow rates of PEG and flow rates of citrate, it is better to work in terms of dimensionless numbers, because this gives you the advantage of being more general. You can use it for any other system. So supposing you want to work with some other system, PEG dextran system or dextran nitrate system, ammonium sulfate system, if you work in dimensionless numbers, you can definitely go and have the use these flow regime maps. So this map is basically same as before, but I've converted it to dimensionless form so that it is more general purpose. Okay, and the Reynolds number is one of the numbers we have. Then you have the Weber number and the Capillary number, and in the table here we have given you some conditions under which you get different kinds of flow patterns. And this is kind of qualitatively similar to the oil water system, but not exactly the same. So there's a difference between this. So by way of conclusions for the hydrodynamic part, what I'm saying is that the segmental flow and the reasonable throughput can be obtained by using a milli channel. In a micro channel, you cannot get your throughput will be very, very less. Your flow rate will be very, very less. So go to millifluidics. The two fluids should be in equilibrium. What I'm pumping in should be an equilibrium, which is the PEG rich and the citrate rich, so that there's no mass transfer. And then I'll get uniform size slugs. Flow regime map of ATPS is similar to that observed in aqueous organic system, because hydrodynamics is similar. Only thing is surface tension is very low. And use of ATPS helps us develop a green process for novel applications, because I'm not using any organic liquid. My process is green. Everything is aqueous. Okay. So now I just want to spend a little bit of time on an application of this ATPS system. Okay. And the precursor that I'm using is silver nitrate. The accelerator, because you use sodium hydroxide, because in an alkaline condition, you will get the higher rate of reaction. We are doing this at room temperature. We are using PEG as a reducing agent. We can also use trisodium citrate as a reducing agent, but PEG as a reducing agent is faster. It takes me 35 minutes, whereas in the citrate it takes 200 minutes. It's a much slower reducing agent, and therefore all the synthesis is performed in the PEG solution as the reaction time is less, so reaction is fast. So we use PEG as the reducing agent, and it's possible. So you want to get your product as quickly as possible, right? So you use PEG as a reducing agent. And what we want to do is we want to synthesize the thing in PEG, and we are going to form the two-phase mixture by adding trisodium citrate for phase separation and trapping the particles. So this is something which I want to talk about. See, the silver nanoparticles that we are synthesizing, they can be in the bulk. So what we want to do is we want to see if I can recover the silver nanoparticles. I want to trap it at the interface. Okay, so this is something which we want to do. Silver nanoparticles in this is in ATPS. Okay, let me just see what I have here. Okay, here. So if you, I'm comparing here synthesis using pure PEG and pure TSC and PEG rich and TSC rich. In the continuous single phase, so first of all, single phase means I'm pumping in only the PEG liquid and doing the synthesis in the single phase where I have my laminar profile. Okay, synthesis in pure PEG and then adding the pure TSC for phase separation, because I'm adding the pure TSC to get two phases. Okay, and this is one way, that is I do the synthesis in single phase and then I do the mass transfer. That is, I first have reaction. Okay, if you look as a chemical engineer, if you think about this, what are we doing in this first case? We are having a reaction where the synthesis is happening in the PEG phase, then I add the TSC phase, and then I have the mass transfer occurring. In the other case, what we have is we have a PEG rich and TSC rich phase. We have the mass transfer between the PEG and the citrate. Everything is in equilibrium, and then the reaction takes place. So the two-step, on the upper thing, I'm having two-step process. In the bottom one, I have mass transfer and reaction occurring simultaneously. So I can add pure PEG and pure TSC, but what will happen is the slugs which are formed are not uniform. So it is better to use PEG rich and citrate rich phase as my reactant. Then I get uniform size slugs. So basically there are different combinations by which you can do the silver nanoparticle synthesis. And the one which gives you uniform size slugs is the fourth one at the bottom. Okay, and we want uniform size slugs. So I just want to show you that you can do this in different ways, but we are preferring the fourth one. And single phase. So how would you go about doing the reaction followed by the mass transfer? You add the pure PEG with the silver nitrate, pure PEG with the sodium hydroxide, then you mix it together. So basically, I want to have my reaction in the microchannel. So I'm not adding the sodium hydroxide in the same channel as the silver nitrate. The reaction occurs only in the millichannel. If I add PEG, sodium hydroxide and silver nitrate in the same syringe pump, reaction will take place in the syringe itself. I want to avoid that. You pump it. So this is the reaction step. Continuous reactions taking place in the single phase because everything is only PEG. Then what I'm doing is I'm contacting it with trisodium citrate. Okay, I add pure trisodium citrate in the beaker to this beaker containing the PEG and the silver nanoparticles, and you see that I have a two-phase mixture, and the silver nanoparticles are getting trapped at the interface. That's what I'm seeing on the right. So this is the first case where I have reaction followed by mass transfer. In the second case, continuous single phase thing, I need to get a PEG rich and a citrate rich phase. So first what I do is I mix the PEG and the trisodium citrate in that conical flask, and I allow it to equilibrate. So now equilibrium is occurring because of mass transfer. So everything is equilibrated, and I have a PEG rich phase and I have a citrate rich phase. Okay, so this is the mass transfer step. I have not added any silver nitrate and this thing so far. Now I will add the silver nitrate and the sodium hydroxide. These are my reactants, which the PEG rich and both are PEG rich. I added to the this thing my millichannel. I have my reaction taking place, and then I add the trisodium citrate and do the trapping of this thing. So the difference is I'm using PEG rich, the equilibrated solution, not the pure PEG. So what is the difference? when I mix pure PEG and citrate, there's some overall composition above the binodal curve. I'll get my two phase. The composition of the two phases are my equilibrium compositions. Okay. Now, the other option that I have is continuous two-phase synthesis, continuous synthesis with the pure PEG and pure this thing. So here, what I'm doing is I'm adding the pure PEG and pure silver nitrate in one T junction, and then I'm contacting it with the dry sodium citrate, and the reaction now occurs in a two-phase flow. But the problem is now the slugs are going to be not uniform. Okay, and because of the slugs are not uniform, the slugs are all going to behave as different microreactors. And if they behave as different microreactors, the size distribution of the nanoparticles formed is going to be very poor. And this is going to be something which is not desirable from the point of view of the efficiency when I'm going to develop an application using my silver nanoparticles. Okay. And this is the last one, which is the best one, where I am adding the citrate and the PEG first. Both of these are aqueous phases. I get an equilibrium. The top phase is PEG rich, the bottom phase is citrate rich. To the PEG rich phase, I'm adding the silver nitrate. To the PEG rich phase, I also add the sodium hydroxide because I want it to be alkaline. Okay. And so now the silver nitrate and sodium hydroxide are basically getting mixed in the first one. Then the two T junctions here. First T junction, the PEG rich silver nitrate mixes with PEG rich sodium hydroxide. In the second T junction, this mixture is contacted with trisodium citrate, which is my reducing agent, which is used for forming my slugs. Okay. So now the role of the citrate is not for reducing, but for forming the two-phase mixture. And I want my reaction to be occurring in the two-phase region. So that's the whole purpose. And then I have the silver nanoparticles are going to be getting trapped at the interface of the slug. And so the silver nanoparticles are not going to be in the bulk liquid. They are going to be in the interface. Okay. So this is an advantage of using this ATPS system. That is, I'm concentrating the silver nanoparticles automatically. Otherwise, these silver nanoparticles are going to be in the bulk, and then I have to figure out a way by which I can take out these nanoparticles, or I have to use the silver nanoparticles as they are in the liquid. And because I'm not using any organic liquid, I can use this for bio applications, for drug delivery and things like that. Okay. This is basically a characterization of the nanoparticles. The one way to characterize these nanoparticles that you get is by using this LSPR spectrum. And so there are totally four curves here. The first two are when you are doing continuous single phase and continuous two phase. Basically, you see a peak at a wavelength of about 400 or something, okay, of 450 odd. So the presence of this peak basically shows you that there are silver nanoparticles present. The sharper the peak, the more is the amount of nanoparticles. The lesser the spread, the better it is. So I'm just trying to show that whatever method we have used for characterizing for synthesizing the nanoparticles shows this thing. So if you use the PEG-rich phase, it has both PEG and THC. the citrate. And so both act as reducing agents. One is fast, one is slow. Therefore, you get a broader spectrum. In two-phase synthesis, silver nanoparticles are redispersed in water, hence absorption is normalized. Okay, that's basically what it is. After doing all this the synthesis, you can characterize the particles by looking at the TEM images, and you can look at the size distribution, and you have to decide for your particular application whether you want to is this distribution that you're getting good enough or not good enough. Okay, so basically these are the steps for an application. I mean, this is basically a summary slide, which I don't think I want to spend time on, but because in a talk like this slide is actually useless. Okay, but it is published in a paper, so you can see what it is. So I just want to come to the conclusion for the final part, the application. So basically, my talk had two parts. The first part was focusing on hydrodynamics, which is the theme of this course, and we were looking at the aqueous two-phase systems, which have a very low surface tension. The second part talked about an application for synthesis of nanoparticles. Okay, and we have basically want to synthesize biocompatible nanoparticles, so we use the ATPS. Okay, we want to do a continuous synthesis. We don't want to batch, because then the variability is going to be less. We prefer dispersed flow, because every slug, every droplet behaves like a stirred reactor, and I will get nice size distribution, uniform size distribution. And there are different combinations you can work on. You can synthesize in a single phase, then you can make it in two phase, or you can synthesize in two phase, and then you can get it. But the important point is the silver nanoparticles are getting trapped at the interface. So at the outlet, you will see that the bulk solution does not contain any silver nanoparticles. So we have a process by which, when I use an ATPS, I am synthesizing the nanoparticles, and I'm also separating the nanoparticles. Okay. Future scope, we can right now I've done the synthesis in the PEG phase, because PEG was fast. The reaction is fast, so you can think of doing it in the citrate phase. Then we can do an phase inversion. There's some details which we can look at, and synthesize using other ATPS systems, PEG and sodium sulfate. You can look at different ATPS systems for doing this, and see whether the method of silver nanoparticle synthesis is very general, whether I can use it for gold nanoparticle synthesis also. Whether, and the PEG comes in different molecular weights, 600, 6000. So is whatever we have studied here, is it sufficiently general for different molecular weights of PEGs? Is it sufficiently general for different salts, for example? Okay, so these are questions which we need to understand. So thank you very much, and I'll be happy to take any questions.
Yeah, thank you, sir. Participants, if you have any questions, you can ask.
Sir, am I audible?
Yes.
Yes, yes.
So, good morning, sir. I'm Pranil from IIT Guwahati. Firstly, very interesting talk. I have a very small question, that is regarding the capture efficiency between the two phases. So, what is the typical Marangoni number, or say the Damphouiller number? Because if you are considering, say, slugs, and the capture happens at the interface, are Marangoni effects pronounced, or sir, the surface renewal rate, how does that also affect the capture efficiency, which can be used for, say, scaling up? That becomes effect factor
Yeah, yeah.
when we are considering the scaling.
So the Marangoni effects are very minimal because there are very strong circulation effects. So there is no gradients of surface tension at the interface. Okay, uh, there is not much. So whatever. So we have a situation where the strong internal, because we are talking about microfluidics, there are internal circulations in the both the continuous phase and the aqueous phase and the dispersed phase. And so, for all practical purposes, the concentration can be taken to be uniform. The change in the shape of the slug is mainly determined by the confinement effect. Regarding Damkohler number, the Damkohler number is quite high because, in the sense that the entire reaction goes to completion. So the Damkohler number is basically a measure of the residence time. Correct? And
Yes.
so we ensure that all the silver nitrate gets consumed. Okay.
Okay.
So that is as far. So you want to make sure that in the reactor all the silver nitrate gets converted to nanoparticles. So that is taken care of by having a reasonably high Damkohler number, and the internal circulation makes sure the Marangoni number effects are not very significant. Okay.
Okay. And in case, say, for example, I work primarily on electrohydrodynamics. So in case we are applying some external field to such, say, millichannels, can we say modulate the interface to actually change the capture efficiency, or is this something you also look forward
So
in your experiments?
right now the capture efficiency is 100%. Okay, but I must tell you that this is only for silver nanoparticles and the spec system which we have chosen, spec 6000. Now, supposing you work with gold nanoparticles, the capture efficiency is very, very poor. Okay, and this capture efficiency is decided by the zeta potential of the particles, the zeta potential of the interface. So if
Right.
you can change these parameters, the zeta potential, then you can definitely improve the capture efficiency. So as of now, we have steady systems where the capture efficiency is either 0 or 100. Okay, so using some modification of the zeta potential, you can make the capture efficiency 100%.
Okay. Thank you
Okay,
so much, sir.
yeah, yeah.